When the halogens occur alone, the elements in group 7a, they occur as diatomic molecules. So bromine, for example, all the atoms in group 7a have 7 valence electrons, and so if you were to write those in around the atoms, you would see that they each have one unpaired electron. And so, if you ever have just the element by itself, they bunch together. They sort of bond together into groups of 2. And so you would get, going from the top to the bottom, you'd get fluorine, chlorine, bromine, and iodine. They're all diatomic. Whenever they exist in their elemental form, they exist in groups of 2, molecules with 2 atoms in them. Okay, so what we're going to do is we're going to take those halogens all by themselves, and we're going to add them to a pi bond. Now, usually this is bromine, but you could also do this with chlorine or iodine. And if you were to analyze this, let's choose a new alkene. If you were to analyze this just from the perspective of nucleophiles and electrophiles, you could say, okay, fine. The pi bond here, like we saw in hydrohalogenation, in acid-catalyzed hydration, in oxymercuration, demercuration, even in hydroboration oxidation, that pi bond is nucleophilic. But where is our electrophile? After all, bromine and bromine, or whatever 2 halogens you're using, they have the same exact electronegativity. So that bond is not polar. Neither atom is pulling electrons to itself more than the other one. It's actually perfectly non-polar. So how does that nucleophile find anything to attack in this molecule? And the secret to that has to do with the size of bromine, and in general the size of the halogens. Aside from fluorine, which we don't see reacting very much because it's very small, it's around the size of a hydrogen atom, the halogens below fluorine, so chlorine, bromine, and iodine, are enormous. Chlorine is the size of a methyl group, so that's 4 atoms, carbon and 3 hydrogens. Bromine is even bigger, and iodine even bigger than that. And what that means is that makes them polarizable. If you think about a bromine atom, let's say, imagine you have these 2 big fat bromine atoms here. There's a lot of room in the atom. When the bromine molecule gets close, as it bumps around randomly in a solution, as it gets close to this pi bond, it feels the electrons in the pi bond. Well, there's plenty of room for the electrons to move around within this single atom. Let's focus on the bromine atom that's getting close to that pi bond. When that gets close to that pi bond, the electrons all run away from the electrons in the pi bond. The electron density gets much higher on the opposite side, and that side becomes slightly negative. And the other side, where they're all fleeing, where the electrons are being repelled by the pi bond, that side becomes slightly positive. In other words, you're able to induce a dipole, an end of the atom that's slightly positive and an end of the atom that's slightly negative. That's 2 ends, that's a dipole. You're able to induce a dipole. Pole is just another term that means end, like the North and South Pole are the 2 ends of the Earth. So when you can induce a dipole, the atom is called polarizable. Because bromine is so big, it is very polarizable, and it's able to induce these dipoles, which creates a partial positive charge that the nucleophile can attack. So if we get rid of this picture and we just think about the atom without the whole gigantic space being drawn, as this gets closer, one side of the bromine becomes slightly positive and the opposite side becomes slightly negative, so that the nucleophile attacks the bromine and kicks the other bromine off. And that should be no surprise. Bromine, we know, like all the halogens, is an awesome leaving group. We know that is for the same reason, that it's polarizable. It's gigantic. And so it can take, this bromine here can act as a wonderful leaving group because it can take those electrons from that bond on itself and stabilize the negative charge it has by diluting it, by spreading the electrons out over its enormous space. Okay, so much for this bromine on the right. What happens to the carbon chain and the bromine it attacked? Well, the carbon chain is going to add a bromine on it. And your thinking for this may be very similar to your thinking for hydrohalogenation, where does this first bromine go? You would expect it to go on the less substituted carbon, because if it's on the less substituted carbon, then that means that the more substituted carbon is the one that would be missing the electrons. That would be the carbocation, and that can be stabilized. That's better stabilized the more substituted the carbon is. But a similar thing happens here as happened in the case of oxymercuration, demercuration. In that case, the mercury had a lone pair after it attached, and that lone pair was attracted to the carbocation, and it attacked it. And that same thing happens here with the bromine. The bromine has a lone pair, and so it attacks the carbocation. Now, it creates this sort of triangular ion. It's called a bromonium ion. So this is similar to the mercurinium ion that we saw earlier. This bromonium ion, the bromine has a full positive charge here. It's missing. It's a formal charge. It has a full formal charge of positive 1. In addition to that, it leans a little bit more toward the less substituted carbon. These bonds are like little springs that are constantly bouncing around, and so there's always a little give, a little leeway in where the bromine is going to be. As it bounces around, the more substituted carbon can handle it going further away, and the less substituted carbon can't. And so on average, the bromine stays closer to the less substituted carbon, and the more substituted carbon has a sort of slight positive charge. And so you form this bromonium ion. Okay. Well, we still have that other bromide, the bromine with a negative charge. We still have that negative bromide ion that's sort of lurking around the solution. So what happens when these are the two species lurking around? Well, there's a clear slight positive charge that the bromide can attack. But notice how it's limited in its ways to attack it. The bromine in the bromonium ion is really big, as we've seen. And so the other bromine, the bromide ion, can't attack this slightly positive carbon. It cannot attack it from the same side that the other bromine is on. It tries to get close and it gets bumped away by that bromine. It tries to get close, bumped away. In other words, it has to attack from the opposite side. This bromide ion has to attack from the opposite side, and that is the reason why this is anti-addition. If you look at the notes for this is anti-addition, and so you end up with the bromines facing opposite directions. If one's coming out at you, the other one will be going away. That's because once the bromine is on there in this bromonium ion, it's too big to allow the other bromine to attack on the same side. So in that case, we end up adding the two bromines, one on each of the carbons, sort of this one going down and this one going up. So this is maybe an unconventional way of drawing that, but I want to emphasize the fact that they added on opposite directions of that double bond. But that's what it is. You add the two bromines, or in whatever halogen you used, whether it's bromine, chlorine, or iodine, you add those, one on each atom in the double bond, and you add them facing in opposite directions. So one will be coming out and the other is going away. So that's sort of the concept behind halogenation, the mechanism behind it. We'll apply this in just a second to synthesis problems in the next video.